Good afternoon and welcome everyone. This afternoon we have Jeremy Kerr as our next speaker, and his topic is server platforms. Experiment with your expensive hardware too. Jeremy will take questions at the end of his talk if there's time, and it will also be in Venulous chat too. So Jeremy is a freelance Linux and open source systems developer working on the kernel, drivers, firmware and plumbing that metaphorically make systems tick. He's also worked on a few clock drivers which literally make them tick too. Jeremy is the technical lead of Code Construct, a small consultancy developing in open source and embedded systems area. Previously, he's worked for IBM's Linux Technology Center on their power platforms, most notably on the Summit, Sierra and Roadrunner supercomputer systems. And we often love to disassemble, rework, reconfigure and improve our consumer devices, but tend to leave the more serious server platforms alone with their warranties intact. Most servers include at least one embedded Linux system for platform control, which we can modify to suit almost any purpose. This talk brings a concept of hackable hardware into the server space. Take it away, Jeremy.
Thank you very much, Kylie. As Kylie has mentioned, I'm Jeremy. I'm a open source software developer from over here in Perth on Wajak. I mostly work on hardware adjacent software. Things like embedded systems, device drivers, the kernel, that sort of stuff. But I guess the common theme is I mostly work on server systems. So my work is based around getting servers running, making them reliable and manageable as well. This talk outlines some of the architectures, some of the design, some of the conventions of typical server platforms, and hopefully forms an introduction to tinkering with those kind of platforms yourself. I guess a bit of a caveat. I don't want to oversell the talk too much here. Some of the things we might want to do probably aren't covered by your machine warranty. So if this talk encourages you into that sort of space, maybe start out with some non-mission critical hardware. I'll go into that in a little bit. While this talk is quite technical, it is mostly an overview. I'll be skimming over quite a lot of detail, but I will be happy to chat. Happy to answer any questions either in this forum or offline or in the many facilities we have for chatting. And this is all basically public information. The specs and the details are all available somewhere online, whether it be in hardware documentation or reference code and that sort of thing. This talk is kind of a bit of a collation of those sorts of things. So off we go. I guess the main thing here is what do we mean when we're talking about a server? What differentiates the server from our client machines, our phone, that sort of thing? There is the obvious stuff. We have higher throughput, higher reliability. But then I guess what I'm concentrating on here is more of the management functions, the side of things that enable us to have large scale deployments of servers, have things managed easily in a way that people generally have their servers set up. So that's what I'll be focusing on here, the management side of stuff. And as an example of some of the hardware that's available, none of this is particularly fancy or new, but this is a spec sheet from an Intel product. As we can see in the third feature at the bottom, it mentions an integrated BMC with IPMI. We'll kind of go into what that entails in a little bit. As another example, this spec sheet is from a Supermicro server. We see here it's mentions the IPMI thing again, and in this case we have a reference to some specific hardware, the AST 2500 BMC. We also see that it's in the VGA section as well, and that's a bit curious. We'll go into why that might be the case a little later on in the slides. And as a third example, we have this one from a Taiwan machine, which mentions again this AST 2500 device, and this time with a couple of bits of functionality that provides the IKVM feature here. IKVM stands for keyboard video mouse, not kernel virtual machine. We like to overload our acronyms here. And some of the a reference to the RPMI again. And this is one of the interfaces that you'd use to manage your server in one of these large scale environments, or even small scale if you're into some sort of automation and that sort of thing. So focusing down onto the BMC, what is this BMC thing anyway? In this case, the acronym itself probably isn't too useful. It stands for a baseboard management controller. But what does it provide? How does it work? What does it usually do? And what else can we do with it? So the BMC is here to provide the server style functionality of our machines in terms of that set of management functions that I referenced earlier. The kinds of things really that people expect for effectively running more than one machine, potentially tens of thousands of machines. So things like power control, being able to turn your machine on and off, always handy. Being able to access the machine remotely, do any debug, do any monitoring, all that sort of stuff that would expect to have a server effectively running whatever workload we want to have. So we tend to think of our servers as a kind of a single entity, an atomic block of stuff that we do our workload on. It may have configurable storage. We may want to add and remove network interfaces, work on modifying the server itself to run the workload in whatever way we want. But roughly, all of this is for the same purpose of serving your website, serving your database, whatever that sort of thing. But if you sort of look a bit closer, we have something more like this. Or we have two fairly separate domains, two separate processing entities, if you will, of the host, which in this case is the obvious one. This is where you run your stuff. This consists of your CPUs, your network devices, your storage, all that sort of thing. And then off to the side here, we have this less mentioned device, the BMC, the baseboard management controller, and this is providing again those management functions. Throughout this talk, I'm going to differentiate these two devices, referring to the host and the BMC as fairly separate things. And that'll be the terminology I guess we're going to stick with here. Having the host, if I mention the host, that's the normal CPU that you're talking about. So these two entities, these two processes provide a different set of kind of external I/O to the rest of the world. But it's not always obvious where that division is. There's just a bunch of sockets on the back of the machine. It's not clear who's controlling what, if one's on the BMC, if one's on the host, and that sort of thing. And we'll go into that further along in the talk today. As I sort of implied, there's some of the things that we think of as standard that you would just connect your monitor or your serial port to can actually be provided by the BMC on various platforms. Now, of course, because we've got two different devices here, we want to have some way of interacting between the two. We have some internal communication between the host and the BMC. We'll go into some details there as well. There's a large variation between how that is implemented, what sort of interfaces exist there. And that is really governed by the design of the platform and the hardware design and the firmware design as well about what happens between the host and the BMC, how they talk to each other, how they interact, the protocols and the hardware interfaces involved in those two. But speaking about the variation here, I think we can kind of classify that into a bit of a spectrum here. Different platform designs certainly have different ways of management. And so we have this spectrum on the interactions between the host and the BMCs, and that defines also the dependencies between the two. So on the left-hand side of our spectrum here, we have the simpler interactions, where there's less dependency between how the host runs and how the BMC runs, and potentially less complexity of the channel between the two of them. On the right-hand side, we have more complex interactions, more complex dependencies, and just more dependency in general, where there's more reliance between what the host is doing, what the BMC is doing, and what sort of coordination is happening on those sides. And that reflects the complexity of the firmware stacks on both of those. So as a bit of an example, on one end, we have the simpler interactions. So in this case, an example platform might be, let's say, an Intel reference design, and they generally have a typically rich management engine here, which controls a lot of the platform hardware itself, and that exists on the host side of things. So the BMC doesn't need to worry about a lot of the more complex hardware dependent sort of functions, and the interactions between the two of these are fairly independent. For example, if the BMC is unavailable, the system still works, and perhaps the BMC is just providing some augmentation to the server's functionality by letting you turn it off and on remotely and grabbing a console. But there's less of a coupling between the BMC firmware and the host firmware, and they can run fairly independently. In the middle of our spectrum here, we may have moved some of the platform functions from the host into the BMC, and as a consequence of that, making the interactions between the two a bit more involved and a bit more dependent on each other. So an example here might be that the host performs more of the BMC performs more of the hardware management. It might do the cooling or the thermal control of the platform. And in this case, if the BMC is unavailable, the server is still functional, but it may be slightly degraded somewhat. So for example, in our cooling case, if the BMC was to crash, the platform can still keep running, but maybe it's ramped up to all its fans, or maybe it's throttled the CPUs a little. So there's a bit more interactions compared to our first example, a bit more complexity, but there's still sort of fairly separate entities. On the extreme end of this scale, we have more core platform management functions being moved to the BMC, to the point where the BMC may even be required to be functional to be able to boot the machine. So there's this high dependency between BMC and host. If the BMC is unavailable, the system may not be functional at all. Of course, there's caveats there. We may have scenarios around being able to reboot the BMC without affecting host behavior, but those sorts of caveats have to be carefully managed. There are periods of time where the host and the BMC are certainly not independent, and we need to coordinate tightly between these two entities. And that the place we put our platform on this scale is really dictated by the platform architecture, the kind of functions that are required from the server, and that has various sort of consequences on the firmware stacks and the type of code we're going to be running here. So in our sample hardware, we made reference to this AST2500 device. This is a little chip provided by a company called ASpeed. It's probably the most common BMC device at the moment, or the class of BMC devices. And we saw it mentioned in 3 of those server specs earlier. We're going to go into a bit of a detail about the hardware itself, but as a caveat, this is picking one particular device as an example. There are quite a few others, but they're quite specialized in what they do. So they kind of all fall into a general category of BMC hardware, which follows some fairly common conventions, I guess. So the AST2500 is an ARM system on chip, low power ARM device, low power in power consumption and I guess processor power as well. Also contains some hardware features for our BMC specific functionality. So going on to the hardware, this is from ASpeed's own public site around describing the AST2500. We see it has a little ARM11 CPU running at 800 megahertz. Has a bit of RAM. The RAM is provided off chip, so as with most things, you have your RAM device, and we can get up to 1 gigabyte attached. There's a bit of flash memory on board for holding your programming data, and we're talking about how that sort of helps us a bit. But in general, this is roughly I guess a Raspberry Pi Model 1 type spec. In terms of the core of the BMC itself, it's a kind of little low power computer that lives on our server and does our management stuff. But by far my favorite function or listed in the BMC specs is certainly this one. The BMC is, in fact, yes, a BMC. We'll cover sort of what that entails, talk about what it means for this thing to be a BMC in a little bit. And of course, being a little device, we need a software stack, right? We need an operating system. And this is a Linux conference, of course. So we run Linux. And even better, we run an upstream kernel on these devices. That's very much to Joel Stanley's credit. He's the maintainer of the ASP architecture support. And he's got a very, very solid upstream sort of policy on things. So at the moment, you can grab a kernel.org tree and boot it on one of these BMC devices. So going into a bit of, I guess, an example of some hardware. This is a board I've picked up to have a bit of an experiment. This is the Intel S2600 ST board, but it doesn't really matter kind of what I'm covering here. This is some generic sort of design factors about a BMC system. So if we look at the board here, this one's on my desk next to me. We're going to use it in a little bit. But in the bottom left corner, we have some extra devices here. The chip with the squiggly line on it, that's actually our BMC. It's the AST2500. It sits there. It doesn't have a lot of kind of interactions with the rest of the world yet. We don't have any way to plug a monitor into it or anything like that at the moment. So how do we use it? Now what? We have this chip on the board. We don't have much of an interface, but we'd like to use it for whatever for any arbitrary sort of functions. Given it's like a Raspberry Pi, it'd be nice to be able to interact with it like we do, say, a Raspberry Pi. So for a typical Linux-based computer, we'd kind of have a few connections, maybe a display, somewhere to get a console. Two, I guess, general requirements there is some way to interact with the machine, whether it be like a video device and a keyboard or a serial console, that sort of thing. We also need, as a second requirement, somewhere to store our firmware, somewhere to put code on it, provide code to the chip that the chip can then run. So on that first item, the console, there's nothing really obvious. The obvious way to get a console for this little BMC chip on our motherboard here. There's no DB9 port. There's nothing that looks like a sort of standard serial port. But it's pretty common to have some sort of serial output or input present on a board, so that during manufacturing or during debug, we have some way of interacting with that BMC device. So if we look a bit harder on our board, we can see these three little pads next to that sideways A, and it's kind of, they look a bit suspicious. They're sort of standing out there on their own. They look like you might want to attach something to it at some point or populate a header on that. So what we can do is we'll power up the machine and attach a scope to those ports and see if there's something around there, or those ports themselves provide something. So in doing that, I attached a scope to a pair of those pads and see what's happening. Then we can boot the machine and observe what those pads are doing. So in this case, attach the scope, turn on the machine, and we saw basically what looks like a TTL serial output. So that looks like our console. Perhaps we can confirm by kind of decoding that signal. And in this case, it's given us a capital of a pair of carriage return new line characters, which that's a pretty obvious sign that there's actually a serial port here. And then we can assume that maybe the third connection is the data going the other direction, the input into the BMC console. So now that we've found that, we can put a little header on it, give it some names, and then use just a serial adapter to talk to the BMC. So that's our console sorted. As I mentioned earlier, we also need some way to provide code to the BMC. And in this case, we saw in those BMC specs earlier that it has a SPI flash controller. And there are a couple of SPI flash chips for firmware storage on this board, but it's traditional to have two, one for the host firmware and one for the BMC firmware. So we can do a little trick to find out which one's which, and hold one of the chip select lines of each of the devices low, and see which one of those held low will prevent the BMC from booting. So after doing that, I found that this other one that's down near the bottom of the board, which is now attached to this programmer, was the SPI flash for the BMC, So just a couple of little soldering connections there gave us a way to flash the BMC chip and then control which set of code, or which control the code that the BMC is running. It's possible to do this without a dedicated programmer on the device. You can often net boot and or flash the BMC from the BMC itself. But this gives us a bit of safety in that we can, if we completely brick the machine, we can reflash without any dependence on the BMC being functional. And that device connected there is just one of these little bus pirates. I highly recommend them for this kind of work. It's a generic USB controlled I2C serial SPI device, and it allows us to, over USB, reprogram the flash on this chip. But now we've got a way to flash it. What do we actually want to flash on it? What sort of BMC firmware do we want to use here? At its core, this is a Linux machine. So in this case, we want to provide a Linux kernel. And as I mentioned earlier, that's upstream. We can use the def config, the ASP.G5 def config to build us a kernel that works well on this machine. We also need a bit of a user space. My preferred way of building a tiny Linux system is using buildroot. If you haven't seen this before, it's brilliant. It constructs an embedded system user space from source components. So it'll download and build a BusyBox shell, or the compiler first to compile a BusyBox shell, various other bits of system infrastructure to give you a tiny user space that we can run on this BMC. Just enough to get sort of your shell and your basic utilities going. We can also provide a U-boot image, but in this case, it's not completely necessary. We can use the one that's already on the board. There's a couple of builds sort of floating around in the BMC space that might work. I didn't have to flash a new one for this one, but you can do if you want to implement any special functions on the U-boot side of things. We've got our stack here. We've got a kernel, we've got a build root, and potentially a U-boot. Let's try this all out. So what I've got in terms of doing a live demo here, this is a blank slide at the moment, but this is the serial console connected to that S2600 machine that's on my desk. Now I'm just going to power it on. As with any live demos, this is always interesting to see what happens. But what I've done here is just powered on the server into standby state. So there's a motherboard sitting on the desk, serial console connected to my slides, and we've just turned on the power supply. Of course, there's no CPUs plugged into this. There's no host CPUs plugged into this device. Just the BMC. So it's not able to boot the host at all at the moment. But as you can see, we've got this little embedded Linux system running. We've booted that kernel into the user space, and consequently, we have a little shell here that was we've built from buildroot. So we'll log in. As you can see, high security here. The default buildroot image doesn't have any password set, but we have our shell going. And as you can see, we're running this live on the 1st of January 1970, which brings us an interesting point in that the BMC itself does not have its own real-time clock. It started off from second 0, and it has no idea what the time is. Usually on platform designs, the host and the BMC will coordinate. The host might provide initial time to the BMC. That has some interesting factors, which we'll sort of cover later. But what we also have is we have a couple of network interfaces. This is a Linux machine. So let's configure the one of them. We'll just do that. Over the okay, so we've got here we've got our network device brought up with an address, and seeing as we had a gotta look over microphone here. Seeing as we didn't have our time set correctly earlier, we can fix that over NTP. And there we go. As you can see, we are now running this live on the 24th of January. So as essentially, this is just a standard Linux device. Here's our CPU information. You can see it's our little ARM chip. In this one, we have half a gig of memory. We have some network devices. This one has a dedicated port, which is what I'm using here. It's just on my local home network. And as an example of some hardware, we have some I2C buses here. This one has a couple of I2C client devices on this bus 3. But in general, the main thing here is we have our own little BMC machine. It's not doing anything specifically interesting at the moment, but it is a machine that we can provide firmware to, log in, and treat as any other sort of generic computer with firmware. So as I mentioned earlier, we have this BMC yes function listed on the ASpeed ASpeed hardware documentation for this device. What actually makes it a BMC? What's happening between these interfaces between host and BMC? And this is kind of one of the set of special functionalities that the BMC SoC provides, is its ability to talk to the host in all sorts of different ways. As an example, on a host that boots from Flash, boots its BIOS from Flash, that is. So its initial, the BIOS screen that you'll see before your operating system boots, it'll often load that over LPC, over a bus called LPC in this case, and that occurs over this channel between the host and the BMC. Now, when the host wants to read this data, the BMC can read it from a dedicated firmware Flash device. It serves it up back over the LPC channel to the host, allowing the host to boot. Another example is a serial data. So you've got your serial console not for your BMC this time, but for the host. That's actually wired through to the BMC. So the DB9 serial plug on the back of the platform is wired through the BMC. When the host has serial data to write, it'll do it over the LPC bus, and those writes will end up out on the BMC going through the RS-232 serial port on the back of the machine. Now, why do we do it this way? It's to allow, as I mentioned earlier, some of the remote management functions of the BMC. Rather than pushing that serial data out to the physical serial port, we can instead, or as well as, we can push it over the Ethernet interface to give us some way to get that serial data from elsewhere in the world. And this is some of those key functions that we expect from a server, is be able to administer it remotely. We also do the same thing for the video, and this is why we saw the AST2500 device in the VGA section. The GPU on this server is actually connected, is present on the BMC, connected over a PCIe channel to the host. And in this regard, the same in a similar way to the serial, the VGA output is connected to the BMC, and the BMC's GPU feeds the data through that. Again, same reason for doing that as we had for the serial, is we can now feed that video out over the network, providing us a way to get a remote graphical console on the host. So all this functionality requires us some way or multiple ways of communicating between the host and the BMC. I made a reference earlier to the LPC bus, or SPI for newer machines. We have a PCI bus also on those on that channel between the host and the BMC. That provides us the video device, and there's also a DMA engine to allow us to sort of copy memory around if necessary. We have a USB bus between the two. Gives us some way to have BMC virtual devices like a mouse or a keyboard that the BMC can emulate. We have I2C, as I mentioned earlier, a way for the BMC to control on-chip peripherals on the host. We have a GPIO for any kind of signaling, any low-level signals that we want to manipulate from the BMC. And we have some processor-specific buses as well. So the PECI bus connects us on an x86 platform between the host and the BMC, allowing the BMC to do some monitoring and control of some fairly low-level host functions. And an equivalent on open power machines is the FSI bus, and that gives us quite a rich method of controlling what the host is doing. Now, I mentioned LPC a bit earlier. This is, while you may not be familiar with the LPC bus, you're certainly, I guess, familiar with some of its predecessors. So historically, the LPC has been bus has been based on the ISA bus, and still very similar in its usage. Some of these addresses here, the layout of things on the LPC bus are probably familiar too if you've dealt with x86 hardware. So we have our serial port on OX3F8. second serial port on 2F8, and when the BIOS is booting, it'll send postcodes, so little bytes of data out to address 80 on the LPC bus, and the BMC can watch, essentially monitor the boot, and we can ensure that it's the host BIOS is booting as expected. There's also another one at address E4. By convention, we have a facility for IPMI between host and BMC. This isn't the external IPMI interface. This is a way to have communication internally between host and BMC. And another device that's specific to these AST 2500 chips is the LPC to AHB bridge, which sounds a bit suspicious. Sounds a bit concerning to have, essentially deconstructing that acronym a bit. The LPC is the host to BMC bus, and the AHB is the internal bus on the ARM device. By internal, I mean having access to memory, I/O registers, the flash. The official usage for, I guess the recommended usage for this bus is to allow the BMC functions to be exposed from the host without a specific firmware stack on the BMC, without the BMC participating in that access. But a bit of a small detour here to talk about security. If that LPC to AHB device is not configured correctly, we can do some fairly arbitrary things over the LPC bus from the host. And that's essentially the core of this CVE from 2019. I won't go into it in detail here, but there's an excellent overview from Joel Stanley in his LCA talk from that year. And essentially, it's not always an issue. In cases where your host and your BMC have the same sort of security domain, where someone who has root on the host could also quite reasonably have root on the BMC, this isn't such a huge problem. But it occurs more when we have a split trust domain. So, for example, in a bare metal cloud provider, the cloud provider might want to retain control of the BMC where they give complete access to the host. So in that case, this would be an issue if the AHB bridge wasn't locked down in the way that the owner expects. So in essence, be careful with the hardware boundaries here. Consider the likely use cases of what your machine might be doing. That said, back to the BMC hardware. Look at we mentioned kind of different types of I/O from the BMC earlier. We've actually got sort of two generic classes of things here. Internal stuff, where the BMC talks to other things in the platform, like fans, thermal sensors, LEDs, buttons, all that sort of thing. And the external I/O, so things like network, video, serial, etc. All the kind of things that you'd expect from a normal computer. And in sort of putting that all together as an example, we can work through the flow of how power control works on some x86 machines. From our architecture earlier, we had this split host and BMC. The BMC has some internal I/O and some external I/O. And following this kind of set of three classes of I/O interface, the host interface, platform internal, and platform external I/O, we use all of three of those in in turning the machine on. So stepping through this, we would have, let's say, a BMC internal web server or an IPMI server. It receives a request to turn the host on over that network interface. The BMC might do some internal state checks. Is the machine already on? Can I turn the machine on? Do we have the facilities available to do so? And if that's all right, proceed to the next step, where essentially in this class of machine, all the BMC needs to do is just toggle one GPIO and the host will start its boot. It's that signal is literally the same signal as the power button on the front of the machine. The BMC just pretends that you're in front of it and you've pressed that power button for half a second or so. So at this point, the hardware on the host handles the rest of the power up. It'll bring up all the devices, bring up the chips, that sort of thing, and it's fairly self-contained in that regard. But that of course depends on the platform configuration. So once we're expecting it to boot, the BMC can watch some other signals. It can watch the power OK signal from the PSU to see that the host is actually bringing it up. It can also check signals from the host itself. Do we see that the system has exited the S5 sleep state? Is it now up and running? Of course, those event states will very much depend on the hardware configuration, the implementation of the hardware. So once that's done, the BMC can consider the host as booted. I guess the key point here is that no magic is required. This is just a Linux machine, and in doing that BMC function, it's done some fairly vanilla stuff. It's twiddled some GPIOs and it's listened on a bus for some events happening. So even though it is a Linux machine, though, we need some BMC specific software to be running those sorts of things. And the one that I guess has popped up in the last few years and is kind of an interesting thing from the open source side of things is OpenBMC. Of course, an open source BMC talk wouldn't be complete without a discussion of OpenBMC. There's a lot of BMC functionality common between all devices, really, like things like an IPMI interface, a Redfish server, which is the replacement for IPMI. And OpenBMC contains implementations of these common software components. Even if you're not using OpenBMC as a firmware load, though, the community itself has a bunch of great people who know a lot about BMC hardware, and the code itself can provide a hardware reference for whatever platform you might be playing with. But that said, this is a vanilla Linux machine. You can run anything else on it. You can customize it as much as you like, and basically do what suits. There's a link to OpenBMC on the slide. It's fairly simple. GitHub OpenBMC. But because it's a vanilla Linux machine, I would say get experimenting. Have a play with customization. See what sort of external interfaces you might want to implement. Port to specific hardware if you like. In general, I would suggest starting with some test hardware, possibly something that's not mission critical. And you want to have some way in general of recovering if you've made your BMC not boot. So protecting it from becoming a brick protection, something like an external flash programmer to allow you to reset to a known good state. And of course, make sure it's not running your important workloads. In terms of the platform configuration, really, I'd suggest starting on hardware that has a simpler interaction with the host, so you don't need a lot of stuff to be working for the machine to be usable. So start on the simpler interaction side of things. If you can have a machine that just requires a single GPIO to turn on the host, that makes things a lot easier to start with. Cool. I've got some resources here. If you're interested in getting going, of course, as I said, I'll be open to chat after the talk for some details if you like. I see we've got some questions from the crowd here. I can take those directly. The first one here is, do any of the BMCs with KVM style console support expose those in a usable way from a custom BMC code? I'm not sure what you mean by usable way on the BMC, and which sort of code stacks we're talking about here. In general, the BMC is able to read the frame buffer on the hardware side. It's able to read the frame buffer of the host and export that however you like. I can't really speak to existing BMC firmware, but it's certainly possible to, it's a Linux machine. You could do whatever you like with those pixels. I hope that understands it. Sorry, I hope that reflects the question correctly there. If we have time for a couple more, Kylie, we can.
Yes, we have got time for some more questions.
Sure thing. Is it possible to access the BMC from the OS? Now, it depends. It shouldn't be, or it should be quite well controlled, or it should be designed in a way that is an intentional thing to do. You can often have a channel of performing specific commands between OS and BMC, but that is generally something that needs to be quite tightly controlled to preserve those split trust domains when necessary. Another one, what do you have to get I2C detect going on a regular PC server? On mine, -L gives nothing. I can certainly chat to you about that after the call. Essentially, you need an I2C adapter present for that to work. And a final one here. Could I flash OpenBMC or UBMC on a Supermicro server and expect remote display support? Or is this more just for curious hardware hackers at the moment? Possibly. I know that there is some work going on Supermicro servers at the moment for OpenBMC, but it'll depend on how close your platform is to the ones with that implemented. The remote display support is fairly generic across BMC hardware, so you might have some luck with that. But if there are interactions that depend on parts of host firmware that haven't been accounted for in upstream OpenBMC, you might be having a little trouble there. But certainly happy to help out if you want to chat specifics soon. I think that's the end of the questions, Kylie.
I'm not sure if you saw this one, Jeremy. It's have you looked into UBMC, the URoot-based BMC project?
I have seen it briefly. I know there's a couple of tiny BMC implementations too, which is great. I'm not sort of specifically advocating for anything at the moment, but yeah, there's a lot of not a lot of. There's a few little stacks that might be useful for starting off with as an initial BMC implementation. So yeah, certainly have a look at things, use them as references, build on them if you like. But yeah, just get experimenting.
Okay, thank you very much for your talk today. I think that's all the questions that have come through. So we'll finish up now.
Thank you, Kylie. Thanks all.